wave your credit card in the air. Don't give away any government secrets. And don't hit anyone. That's it, because it's now going to be on the internet. By the way, we are an all-volunteer organization. How many people have been here before? How many people have?
Doors open.
Well, you know we are, but there is a donation box in the back. If you like what you see, you can give us a donation. If you don't like, you can be bad to us and give us less of a donation. But in any case, that's how we survive on membership and donation, and donation would be much appreciated. It's cloudy out. Yeah, this is life on planet Earth. So relax, be comfortable. If you haven't seen the scopes upstairs, they're not going anywhere. So after the talk, you can go up, take a look. Tonight's speaker. Let's see. Is there anything else I forgot? No. Tonight's speaker is a grad student at the University of Georgia in the Physics and Astronomy department. And you know how I just envy your youth. Because you see people, the reason I envy his youth, you see, it's because this is the time in Mitch's life when a young man's heart turns to mass outflows in active galaxies and physical implications of the gravitational wave memory effect. You don't think he's got a life? What a life! Isn't that great? Well, that's the topic, actually. He inherited his mouth. And what he's going to do, this is Mitchell Revalski. What he's going to do is he's going to explain what on earth this is. And he also encourages questions throughout. So if you have a question, don't let it go too far, and just raise your hand or yell it out, and he'll be more than happy to answer. So please, everyone, welcome Mitchell.
All right. Well, thank you very much for the introduction. I'm so happy that I was able to be here tonight. So I grew up in this area, just over the hill. I went to Wood Glen Middle School and then Voorhees High School, and I'm fortunate enough to have a few of my teachers in the audience tonight who were definitely influential in me standing here tonight. So what I want to do is go ahead and kind of give you a summary of the topic that I've been researching so far in graduate school. So I've been down at Georgia State University for a little over a year now. I'm really starting to get into my research, and I'm really enjoying my project, so I want to go ahead and share it with you tonight. I don't want to just dive right in with anything too crazy, so I want to start and make sure that everyone understands what we're talking about, and then I'll share a little bit of my research results so far. As John mentioned, if you have questions at any point, please feel free to raise your hand, shout out. If it's something more lengthy, I'd be happy to talk with you afterwards. So just sit back, relax, and again, feel free with questions at any point. So I like to jump in with what I call the what, the why, and the how. So the what being, what are active galaxies and mass outflows? Before I start talking about all the details, what are they? What are these mass outflows? What are active galaxies? What are their characteristics? What defines them? Then go ahead and say, why are these important to study? Because if we're going to go ahead and take time to study them and devote our telescope time, we want to know what's important. Why should we be interested in studying this? So then following that, once I've convinced you that this is the greatest thing since sliced bread, we want to go ahead and say, what are we actually going to do to study this? What are the techniques we use? What types of telescopes and instruments do we use? How do we go about doing this? Once that is all covered up, we want to talk about what we've learned so far. So what we've learned in this field, in my particular niche of the field, and then where we're aiming to go. So at the end of the night, we have this crazy picture of a galaxy and black holes and all sorts of stuff going on. And we'll come back to the end of the night, and hopefully we'll all have a much clearer understanding of what's going on here. So before we go into active galaxies and all their details, let's just start right at the beginning real quick and talk about normal galaxies. So our galaxies are collections of stars and gas and dust and all the little tribblings of everything else, of planets and moons and us and so on and so forth. And they come in a variety of types that we usually put together in this, what we call a Hubble tuning fork. And we have big elliptical galaxies that are big and round and have lots of old stars, not very much gas and dust. And then we have other types of galaxies, which we believe are more like our own, spiral galaxies, which are flatter and have lots of young stars orbiting around the center of the galaxy, lots of gas and dust, ongoing star formation, all sorts of activity going on. And we break them up depending on their characteristics. We have ones that are just spirals that are all nice and wound up. We have some that have bars going across the center, and then we have some that are irregulars that don't fit into any of the categories, usually galaxies that have been torn apart and are interacting with other galaxies. So this is kind of the way that we usually split galaxies up. So many of these types, primarily the ellipticals and the spirals, can become active galaxies. These types of galaxies can be active galaxies if the conditions are right. So these types of galaxies are very similar to our normal galaxies. It's just a matter of what's going on in the center. So what we see, what defines an active galaxy, is that they have a very bright, very compact center. The center of the galaxy is extremely bright as compared to other galaxies. In some of the most luminous other active galaxies, we're talking about the entire luminosity of the Milky Way, the brightness of our entire galaxy coming from something about the size of the solar system. And it can be even more than that. So we're talking about all the light of an entire galaxy and then some coming from a very tiny region, all in the center. And the way we think that this can happen is that we have a supermassive black hole in the center. Our observations tell us that at the center of most galaxies, we think there is a very large black hole, an object that is so dense that even light cannot escape. It's extremely dense, extremely small, and everything is being pulled into it. And these have masses of millions to billions the times of the mass of our own sun. So they have an immense gravitational influence. They control all the space around them. They can pull things in. Things can orbit around them. We can have all sorts of extreme physics. So what this does is release a ton of energy, a ton of light. So as stuff is being pulled in, and that can be gas and dust and other stars, it's getting squished down, it's getting squeezed together, it's mashing into each other, and it's squeezing down, it's heating up, and it's just like a glowing iron. It's releasing a ton of energy, a ton of light. And it can release all across the spectrum, meaning if we're further away from the black hole, we might see things like radio waves, and then as we get closer, we can see what we call the visible part of the spectrum, what our eyes see. And then as we get closer to the black hole, we get the more extreme energy. So we can have ultraviolet, which we get from the sun that gives us sunburn. We can get X-rays, which we use to take pictures of our bones. And then moving on into some of the highest energies that we can see. So this can yield a bunch of different types of active galaxies. And the best picture we have right now is that it depends on how we see the galaxy, what the orientation of the galaxy is. So some active galaxies are extremely bright in the center. Some of them have these relativistic jets of material that's being shot out of the center of the galaxy at nearly the speed of light. Some of them are much more quiet, much more docile. And what we think right now is that most of those differences are due to how we're viewing them. So if you're looking right down the barrel of the gun, so to speak, right down this jet of material, it'll look extremely bright, extremely violent. And then as you move more and more towards looking through the edge of the galaxy, you have more dust, you have more gas obscuring your view, and it's harder to see what's going on. And that can change what we observe in the long run.
Mitch,
Yes?
how does that relate to quasars, like 3C273?
Excellent question. So we can break the active galaxies into a number of classes, the most powerful of which are normally what we call quasars. And these are galaxies very, very, very far away in the early universe. And those basically look like a point of light. So they almost look like a star. And they're extremely luminous. So even though they're far away, we can still see them. And that's where they get their name, either being a quasi-stellar object, because they look like a star, or a quasar, meaning they're radio loud. So we're getting all this radio emission that you shouldn't see from a star. So that was some of the first indications that these are a different type of object. And then as we get closer and closer to us, to the more recent universe, we see usually lower power active galaxies, things that are not emitting quite so much energy. Any other questions before we move on here?
Yes. Where does our Milky Way galaxy fall? Is it a active galaxy?
That's a good question. So what's going on here is we have material falling into this big black hole. And so even for the most normal, quiet, quiescent galaxies, they can still have a little bit of material left over that's still falling in, or maybe a star that passes too close by. So if you go to the very, very faintest end of the active galaxy spectrum, you could, in a way, consider the Milky Way to be active. It's just extremely, extremely, extremely low. The amount of material falling in and the amount of energy being released is so minuscule compared to these bigger galaxies. Excellent question.
And this is a bit off the point, but I believe our solar system is located about two-thirds of the way out from the center in one of the spiral arms. Is that correct?
Yes, our solar system is located roughly 27,000 light years away from the center of the galaxy, which is roughly two-thirds of the way from the center in comparison to what we can see in terms of normal stars. Mm-hmm. So we have this pretty artist picture, but now we can look at real, true images of active galaxies. So on the left side here, this is a famous object, Messier 87, and this is a large elliptical galaxy. And what we see in this object is this jet of material being shot out into space. And this is not an artist representation. This is a real image. So it's been enhanced and the contrast has been played with in order for us to be able to see it better. But what we have is this stream of material that's being ejected off the center of the galaxy, being driven away from the black hole. And as the material goes along, it can slow down, it can interact with gas and dust, and we get these bright spots from material smacking into other material, an extreme amount of radiation being released. And then on the right, we have something what we might consider more typical for our nearby universe. This is a spiral galaxy, the famous M51, the Whirlpool galaxy, and believe it or not, this is a type of active galaxy. At the very center of the galaxy, we have a very bright core that's emitting some of this radiation, not quite as powerful as some of the other types, but an active galaxy nonetheless. So in order to set the scene and get a mental image of what's going on so we can move forward, spiral galaxies, they can range in size. Some of them are roughly 5 times the size of the Milky Way. Most of them are smaller. So in quote-unquote average size for a spiral galaxy might be 100,000 to 200,000 light years. So if you're standing on one end with a flashlight and you turn it on, it'll take somebody on the other end 100,000 to 200,000 years to see that. So galaxies are relatively large. Then a couple of the regions that we call here that I'm going to talk about a little bit more soon, these are the regions where we see this emission coming from these active galaxies. And basically it's gas that's heated up and emitting lots of light. So the outermost reaches of this, the furthest out that this kind of reaches, is what we call the narrow line region, and this is on the order of 300 to 3,000 light years. So to give you an idea of the scale we're talking about here, there's a little green box there, so it may not look all that impressive. We are talking about the very centers of these galaxies. Then the higher energy regions and the giant supermassive black hole itself are even smaller. Those of you with excellent eyesight can see there's one red pixel in the center of that image. Everything else here fits within that one pixel. So we're talking about regions that are on the order of the size of several thousand solar systems, all the way down to the black hole itself, which is about the size of the Earth's orbit around the sun. So we're talking about millions of solar masses all crammed down into a very small space about the size of the Earth's orbit around the sun. So the region that I'm going to be focusing on tonight is in this green box here, basically the outermost reaches of what we can see these active galaxies producing. So again, these are very approximate numbers. For those of you on YouTube fact-checking me, please keep in mind that these are some approximate numbers, but it gives us an idea of the scales that we're talking about here. So I'm interested in these further regions because we can actually see their extent. We're not looking at a little point of light. We can actually see as it propagates out into the galaxy. So these are 2 more examples. We can see we have all sorts of different types, and the types that we're going to be focusing on tonight are these ones that have these bright centers that are much, much brighter than the regions around it. So now we can go ahead and talk about mass outflows. So these active galaxies are producing an immense amount of radiation. We have all this light and all this material trying to escape, basically, because we have lots of heat, lots of energy. Everything's trying to escape or be sucked into the black hole. And what this means is pressure. It's basically a type of wind. We have all this radiation and it has to go somewhere. If it's not going into the black hole, then it's trying to escape out. So what we have is a tug of war here between the black hole and all the energy that it's producing. Gravity is trying to pull things in, and the radiation is trying to escape out. So there becomes a balance here, because this means the black hole can't just eat as fast as it wants. There's some limit to how fast it can eat this material. So we're driving material away from the center of the regions of the galaxy, and why this is important is because it regulates how fast the black hole can grow. If the black hole can't just eat material as fast as it wants, there's some rate of growth, some amount of time it will take to get bigger and bigger. So of course, why is this important other than for just the black hole? It's for galactic evolution in general. We think that the vast majority of galaxies were active or more active than they appear now at some point in their life. So this is important in understanding how a lot of galaxies evolve over time, because we're looking at how we're regulating how fast the black hole can grow, and also the bulge, which is basically the large center regions of the galaxy. Since we're driving material out, this can either trigger star formation, it can cut off star formation, it can move heavy elements around in the inner regions of the galaxies. And some examples of this are a galaxy here where we have a bright center, and then we have this ring of star formation, material being compressed and then triggering star formation. So we're really talking about how the center of the galaxy is evolving over time. So now the question is, how are we going to determine this? How are we going to investigate it? So before I move on, are there any questions on this section about what we're talking about with the evolution of the galaxy?
You had mentioned before about the size of a supermassive black hole being approximately the size of the Earth's orbit around the sun in diameter. The diameter would then be therefore about 186 million miles approximately?
For something roughly the mass of our black hole, yes. So it can get quite a bit bigger than that, but for roughly the size of our black hole, yes.
Okay. Well, what is the minimum criteria for a supermassive black hole in terms of mass or size?
That's a good question.
Is there any standard?
So the question was, is there some sort of minimum that constitutes a supermassive black hole? So we have roughly 3 variants of black holes. The first are stellar mass, which we get when massive stars die, and they're usually in the range of 8 to 10 to 15 to 20 solar masses, so they're on the order of the size of the sun, a little bit bigger. And then we have intermediate mass black holes, which are several hundred solar masses, and the truth is we don't necessarily know where all those come from, and they're extremely rare. And then the next biggest ones are the supermassive black holes, and essentially we only find them in the centers of galaxies. So that's usually the biggest criteria, and they tend to be at least millions of times the mass of the sun. It's a good question. Any other questions? Yes.
You showed us a picture of energy going through like a jet stream.
Mm-hmm.
So what makes it go as a stream instead of just radiate in all directions?
Yes. So looking at the jet in M87 here.
Yeah.
So that is a complex question which has been under investigation for a long time. So the question was, why is it that the jet of material appears to be going out in such a nice straight line? Why isn't it just going everywhere? And in this case, what we believe it has to do with is the magnetic fields that are around the black hole. So you're bringing all this material in, it's wrapping together, and all the magnetic field energy is also being twisted. And what we believe is that this basically guides the material as it goes out. It makes kind of a funnel for it. And that material is then constricted to that motion. So it makes a very narrow, basically, pencil beam out of the galaxy.
Does that direction always like stay the same for the object? So it's not like, at one point it's going this way and then sometime in the past it went a different way?
That is an excellent question. So for those on YouTube, the question was, do the jets of these galaxies always stay pointed in the same direction? Could they be different in the past? And the truth is, yes, they change. So we've seen examples of what we call swinging jets and jets that turn on and off. So if you look out in the very extended regions of the galaxy, you can see material that appears that it was ejected a long time ago, and then you'll see a large break, and then you'll see a new jet that's coming out. So basically the jet turned off and then turned back on again as more material became available. And the other example that we see is what's called swinging jets, and those are basically jets that appear bent in shape because the entire jet is swinging. So that could be due to a number of things. That could be due to how the black hole is aligned with its galaxy. It could be due to galaxy mergers. All sorts of things can change that. That's an excellent question. So they actually, yes, they can change over time. Any other questions before we move forward? Yes.
Yeah, how does a supermassive black hole actually form?
Ah, that is an excellent question. So how do we actually get this supermassive black hole? How do we get this giant million to billion solar mass black hole at the center of the galaxy? And the truth is, I don't have an excellent answer for that. It is still an area of investigation. So what we think so far is that these could either happen from many, many small galaxies merging over time, or in the early universe when things were first forming, we had some black holes that were there that were able to grow very quickly. So we're actually not sure. The best answer I can give you is we're not sure yet. So that's an excellent question, though. Anything else before we move forward? Yes?
I have heard that if you look further away, and we're talking billions of light years out, you can see further back in time. Now, if these active galaxies, these galaxies in the early universe may have been more active, more prominent, more frequent. Do we see any evidence by looking at the far reaches of the universe? Any evidence that way back, billions of years ago, there may have been a higher proportion of active galaxies than we see nearby?
So that's a great question. So the idea and the question is, as we look further away, we're looking back in time because it takes a very long time for the light to reach us. And so we seem to observe that active galaxies further away are much more powerful. So the question is this something intrinsically different about galaxies are far away? Is this something evolving over time? Is the fraction of active galaxies the same? And the truth is that's also a difficult question because when we look really far away, the only things that we can see are these active galaxies because they're so luminous. So that goes back to looking at how early galaxies formed, how rapidly they formed, and what sizes they were forming in. So we have models and we have predictions as to what the early universe was like, and our observations can make some footing there. We can reach out to some depth. But the truth is, so we're all galaxies, these monster active galaxies, or was it just some? That's still an ongoing debate because, yes, so right now when we look, we only see these brightest ones, and then it varies a lot in maybe that first 1 or 2 billion years as to what the fraction might have been. So unfortunately, I don't have an extremely clear answer for that one either. All right. So now we have an idea of what we're talking about. How are we going to do this? How do we go out and study it? What are the tools that we use? And the astronomer's tool of choice for this is usually spectroscopy, which is basically just the study of light. So this can come in all different forms. In this case, we're studying light coming from astronomical objects. You can do spectroscopy in the lab, in chemistry, in bio. You can do it all over the place. But what we're doing is we're taking the light and we're splitting it up into its individual colors. We're making it basically into a rainbow. We're passing it through a prism or some sort of device that does something very similar, and we're splitting it up into all its different colors, into its different wavelengths and its different frequencies to see what it is that's going on. And what we see is that we get basically 3 different types of spectrums from different types of objects in various combinations. So if we just have a hot object, in this case it could be a light bulb or a star, you name it, and we go ahead and take the light from that object and pass it through a prism or something that splits up the light, what we see is what we call continuous spectrum. Basically we get all the different colors in varying amounts. So if we go ahead and take the light from a star and split it up, we'll actually see all the different colors, and most of the light we're getting is what color the star generally appears. So hot blue stars are actually giving us all the different colors of light, but most of it is coming in the blue. Similar idea for red stars, most of the light is coming in the red, but we're getting all the different colors. So hot objects just give us all the different colors of light. The next type is if we go ahead and just look at a cloud of gas. So this is just gas here that is being excited somehow, and the gas is made up of individual little atoms, and around those atoms are electrons. And electrons are just like people walking up and down stairs. So electrons are on certain stairs, which are their different energy levels. And if a photon, a piece of light, comes by that matches the energies you like, you can jump up the stairs, you can jump up to higher energy levels by taking away that photon. So you're taking away the light and running up the stairs to increase your energy. And then by the same token, it goes the other way. So you can be an electron up the stairs and jump down to a lower energy level, and you can give off a photon. So if all we see is a cloud of gas that's excited, it's sending out light in all directions, we see what we call an emission spectrum. We get very discrete lines, just very specific colors with basically nothing in between, because it's just those very specific steps in energy, those very specific steps in color. And then the last bit is we can combine the two of those. So we have a hot object and light going through a cloud of gas. So we have all the colors, and then the gas cloud says, ooh, I like those certain colors, I'm going to grab those. And then it throws them in all the different directions. So it takes it, and then it lets it back out. Nothing's destroyed, but it sends it in all different directions. So we get what's called an absorption line spectrum. We see all the different colors with those specific little colors missing. And this is the tool that we're going to use to study our galaxies. And the reason that we want this is because it tells us all sorts of different physical characteristics about what's going on. So the first part is it can tell us the presence of elements. So we know what patterns different chemicals make, like hydrogen and helium and oxygen and so on. So we can go ahead and identify what elements are there. We can go ahead and identify what elements that we're looking at, even though they're very far away. The next part is we can figure out how fast that material is moving from the Doppler shift. So if you hear an ambulance go by or a train go by, you hear a high pitch as it's coming towards you, and then a lower pitch as it's moving away from you. Very similar idea with light. If an object is moving towards you, it's scrunching that light up, it's scrunching up the wavelengths, and it looks more blue. It's called a blue shift. And if it's moving away from you, the wavelengths get stretched out. It's called a red shift, and things move more towards the red. So depending on where these very specific lines get shifted, whether they get shifted one way or another, we can tell how fast things are moving relative to us. So that's the first part that we care about. Next part is, which I'm more interested in, is getting the density. So we can look at a gas cloud and say, okay, there's gas there, there's material there, but how much is there? How dense is it? And this can tell us all sorts of different things about the physical characteristics. If there's not a lot of gas there, if it's very spread out, that can tell us one thing. If it's all very compact, if it's very squeezed together, that can tell us something else. And then we can also get the temperature. And the temperature is very important for figuring out what is heating this gas and what the gas is doing as it interacts. And then we can figure out the total amount of mass, so basically how much stuff is actually there. And this part is a little bit harder to do, but that's interesting if we're trying to see all this different material in the center of the galaxy and what it's doing. We want to know how much is actually there, how much actual mass we have. So to do this in practice, when we actually want to go out and do this, we go ahead and look at our galaxy. But if we were to just take our light from this galaxy and pass it through a prism, all the different places on the image would all overlap. All the colors would just get all mixed together. So what we do is we put a slit on the image and basically block out everything else. And then all we're getting is the light from this one specific part of the galaxy, basically just taking one little slice out of the galaxy. Then what we do is take that and pass it through a prism or a spectrograph or a grating, whatever type of instrument we're using to split up the light. In this case, we're using a prism. And then we go ahead and record how bright each of the little spectra are. So what this means is, at each little point in space, at each little point in our image, we're getting an individual little spectrum. So at every little point along the galaxy, we're getting a spectrum, and that can tell us all these different physical characteristics at each point in space along the galaxy. So far, so good. I know I hit you with some heavy stuff here, so any questions at all? Yes?
Wouldn't you also take into account binding rotation? Because it would be able, you would have on one side a blue shift and one side a red shift as it rotates on its axis.
Yes. So a lot of the nitty-gritty details, which I so conveniently swept under the rug, is that this accounts for all velocities. So we have our galaxy turning. The galaxy that we're looking at is turning. Our galaxies are moving relative to each other. Our sun is moving around our galaxy. The Earth is moving around the sun. The Earth is rotating. All of these things stack together. So you have to go ahead and one by one pull out the pieces that you need in order to figure out how fast things are moving, say, relative to the galaxy that you're looking at. So we measure how fast some cloud is moving in a galaxy, but we want to figure out how fast it's actually moving in that galaxy, not just relative to us. So that's an excellent question.
Oh, excuse me.
Yes?
That pyramid represents the visible light spectrum. Is that correct?
Yeah, so the prism represents our spectrograph, which is basically our instrument that goes ahead and splits up all the different light. So we send the light in just as it comes through our telescope, and then we go ahead and we split it up into all its different colors.
And then beyond that is the UV and other invisible light that we don't see.
Yes, so you can do similar things all across the spectrum. You can look in the radio, or in the infrared, in the visible, in the ultraviolet. You can use different parts of the spectrum, but you'll usually use different types of telescopes for that. So it depends on what type of science you want to do, what type of energies you want to look at. You can go ahead and pick and match what part of the energy spectrum that you're interested
And the
in.
blue rays are shorter and the red rays have longer wavelengths.
Correct. Blue is higher energy, red is lower energy. So when we go ahead and do this, we go ahead and we place our telescope on our galaxy, we go ahead and get the light, we split it up, we put it on the detector. What do we see? What do we get? What we get is a mixture of all the different spectrums. So down here is an example, and then we go ahead and make a graph version of it so we can see what's going on. So we have all the different colors going from left to right, and then up and down is basically how bright the light is, how intense the light is. And so what we see is we have this overarching brightness at all the different colors, and that's coming from all the stars putting off all the different colors all added together. And then on top of that, sitting on top of the light from all those stars, we have these very specific emission lines, as we just talked about, coming from different types of gas. So the camera will go ahead and record something like this at each point in space, and then we go ahead and make it into a graph so we can see what different emission lines we have, what kind of continuum we have, and understand better what's going on. So we get this at each point in space, and then we can have all sorts of different types of spectra. So I'm just going to touch on this briefly. This is an example of what we call a normal galaxy. So over here towards me is the blue end of the spectrum, and towards the right is the red end of the spectrum. And what we see is that basically we get all the different colors in little varying amounts. We have all the different bumps in the spectrum because we have lots of different stars. We have some dust and gas that's absorbing light. Basically, we get lots of light where we see light coming from stars, and then it kind of tribbles off. And then as we move up here, we're getting more and more powerful active galaxies. And what we can see is some of the ones that we briefly mentioned, quasars. They have all this light coming out in the blue. They have these big emission lines, lots of energy coming out, and then a whole bunch of different types I'll be happy to talk a little bit more about at the end if anyone's interested. So now we can go ahead and finally dive into the research that I've been doing and use everything that we've talked about to start learning about some of these different galaxies. So my first galaxy that I've been working on is called Markarian 573. That's just its catalog name. It doesn't have a better phone number than that, unfortunately. But this is a well-studied galaxy, but it hasn't yet been studied in the way that I'm doing in particular. So what this is on the left is an image of the galaxy, the very central region. So we can go ahead and put our slit on there with our telescope. So this is the slit that was placed across the galaxy itself using the Hubble Space Telescope. And we can see the center region here. This is about 3,000 light years. So we're looking at, again, a decent chunk, but basically just a coin size at the center of the galaxy. And then we go ahead and take a spectrum. And again, this is just the graphical to help you. On the left is blue and on the right is red. And this is what the actual spectrum looks like. So in order to understand what's all going on in here, we can go ahead and take that image of the galaxy and flip it sideways so it matches up. And then let's look at just those two things. So the idea here is the telescope sees just all the light coming from the galaxy in this one slit here. And at each little point in space, we're getting a spectrum of the galaxy. So over here, if we take the very center of the galaxy, the very brightest point, and we follow that line over, what we're seeing at each point is how bright the galaxy is at different colors. And then as we move up and down, we're actually moving up and down along the image. So what you can see is where there's bright knots of emission, like here in the center, and a bright knot of gas here, and a bright knot of gas here, we get a very bright blob in the spectrum. We're getting a lot of light from that part of the galaxy. And then regions in here where we don't see any bright emission from gas or anything like that, we don't have very much brightness. So moving this way is the different colors, and this way is physically moving along the actual galaxy itself. And so what I've isolated here are three different emission lines. So along the very center, where there are lots of stars, there's kind of this overall gray fuzz, which is just all the light from the different stars. And then we have these three very bright emission lines. And these ones happen to come left to right from hydrogen and from oxygen. And we can go ahead and use these lines to do all the different science that we're talking about. So if we go ahead and take a full spectrum and look at all the different things here, we can see that along the spectrum we have all these different bumps, all these different emission lines, and we can go ahead and use the tools that we've developed to identify what's there. So this is work that was done previously, and I've gone ahead and gone just a little bit deeper to try and identify some of the fainter stuff in there. And basically what this is all the different elements that are in there. So we have things like neon and iron and sulfur and oxygen and all these different elements. And each one of these is useful because it can tell us things about the velocity, about the density, about the temperature. So these are all diagnostics. These are all tools that we can use to go ahead and probe the center regions of the galaxy. This is something very similar, just using a different, basically prism, a different element that spreads the light out more so we can look at finer details. And we have lines from nitrogen and oxygen and even iron lines with lots of electrons ripped off, and that tells us things about the temperature and all those sorts of details. So to give you an idea of what I've been doing in my office behind my computer for the last year, which is where you will find me about 90% of the time, I've been going ahead and measuring these spectra and going ahead and developing tools to actually extract the information that we're interested in, using some tools that were previously developed by my advisor and his previous graduate students, and then rewriting and writing a lot of new software to go ahead and do specifically what we're interested in. So in this case, what I have is these two little lines down here are generated by sulfur. And the reason that those are important is that we know that they are dependent on the density, meaning one of them gets bigger when the density is low, and the other gets bigger when the density is high. And we can predict exactly what the density is, with some little error, based on how strong those lines are. So what I'm doing is using those lines and go ahead and making fits to them to go ahead and see how much light is there, and then measuring along the galaxy what the density is. So is the density highest in the center or out in the edges? Does it go up and down, or does it just go up? Does it just go down? What do we actually see? What's actually happening? Then I've also gone ahead and tried to find the temperature, and then eventually the ultimate goal will be to find the mass. How much stuff is there, and how fast is it moving? So this is where the new results come in. So this is brand new. You are the first people to see this of my work other than my advisor. I'll be presenting this at a conference in January, but you are the first people to see it. So some of this is still a little preliminary. So anyone who's watching on YouTube that's going to go run and tell my advisor about the size of my error bars or something, just hang back. There's still some details to be sorted out, but overall this is the picture that we're looking at. So the first thing is the temperature. And what this is basically along the galaxy, what is the temperature of the gas? And what we see in this graph over here is actually the center of the galaxy. And what we see is that the gas is 16,000 degrees Kelvin. And then as we start going away from the center, the temperature of the gas actually drops and becomes slightly lower and lower as we go. Then we get out into some of the further reaches where we saw these smaller knots of emission, these smaller gas clouds, and it turns out that they're cooler, which might be what we expect, but there's no way of knowing that for sure until we check. The next part, which is the most important to my work, is finding the density. And so in this case, this is the very center of the galaxy here, and what we see is at the center of the galaxy, the density is very high. And what this number means is it's the number of electrons that are just floating around free, and basically how much material is there. So what we see is in the center of the galaxy, it's high, and then it drops off. And then on the edges, again, it starts high, and then it drops off. So if we just go ahead and isolate just the center, if we go ahead and just grab this chunk right here, what we see is that it actually follows a very interesting trend. And what that is at the center it's highest, and then it falls off in this very neat way. And similarly on the other side, other than that one pesky point, but that's science, right? Not every point's going to do what you might hope it does or expect it to do. And so what we see is the density is highest in the center of the galaxy, and then it's dropping off in this very smooth, almost predictable way. We can go ahead and fit what we call a power law to that. We can go ahead and see how it drops off with distance. And so you might say, okay, that's Sure, that makes sense, right? Highest density in the center, getting lower and lower, but there's no need for it to have been that way. It could have been lower density in the center because material is being driven out, and it could be piled up on the edges, or it could go up and down like crazy. So this is actually relatively interesting that it follows this very simple pattern, this very simple way of things happening in nature. Yes.
Is there any idea as to why you would have the aberration on the right like that drop off that's more pronounced than the other? In other words, it doesn't fit the pattern.
It could be,
reasons.
yeah, it could be a number of things. It could be truly intrinsic, that clump of gas is just a different density. It could be an observational effect where some of the gas is being obscured, or there's other gas that's changing what we actually observe. So we'll have to go back and look at that point and see what's going on at that specific point in space.
That electron density represents the dot in the center there is the center of the galaxy.
Yes, so this dot right here is the center of the galaxy,
And
the very brightest part.
Leftmost one is the outer fringes of the galaxy.
Yes, so as we move out, this is moving towards the edge of the galaxy, and this is moving towards the other edge of the galaxy. But again, we're just looking at the very center. So this is really just the very center of the galaxy moving out away from the supermassive black hole.
So it's a relatively small area, actually,
Yes.
in comparison to the whole galaxy.
Yes, in comparison to the galaxy, relatively small. Any other questions before I move forward? Okay. So, to put it all together, how am I going to use this moving forward, and what's the ultimate goal? The next step is to go ahead and make some models so we can go and take all these measurements that we've done of how strong all the different lines are and what elements we see and how excited they are, and we can run it through models that will put back to us the conditions that we're seeing. It will tell us what it thinks the density should be and the temperature should be and all these different things, and we can compare it with our observations. They should agree, but if they don't, that will tell us that we're missing some of the physics there, that there's something that we need to more fully encompass in order to really understand what's going on. So now I've gone ahead and found the density of this gas, so I know how much stuff there is in each little unit area along the galaxy. And we can go ahead and use images of how bright that galaxy is to figure out actually how much mass is there. If you were to go there and have a scale and somehow magically make it work because you're floating around in space, actually measure how much material is there in space. And the reason this is important is we want to figure out the mass outflow rate. We want to figure out how much material is actually moving away from the center of the galaxy. Because we want to know, is this significant? At the end of the day, this ties back to the beginning of, does this affect galaxy evolution? So for some galaxies, it might just be a little bit of material flowing out, doesn't change things on the long scale. In other cases, it might be a lot of material. So this has only been done with this type of technique for one specific galaxy, which is NGC 1068 or Messier 77. It's one of the brightest Seyfert active galaxies in the sky. And what our group found before I started at Georgia State was that there's a lot of mass outflowing. So what this is distance from the center of the galaxy. So it starts at 0 and it goes out roughly to 400 light years. And then on this axis is how much material is flowing out. So what this means up here, the 3 would be 3 solar masses worth of gas. And so this dotted line down here is what we would predict if all the material was just being blown away from the center. If that black hole was controlling everything and it was just blowing gas away from the center, that's how much we should see, this little tiny line down here. But what was actually seen was this huge jump, many, many times more mass. And what my advisor in our group believes is that this galaxy, as the material is being blown away, is actually scooping material up with it. It's hitting other gas that we may or may not be able to see, and it's actually pulling it out with it. So something like 3 solar masses, that may not sound like a whole lot, right? We have billions of stars in the galaxy, but go ahead and add this up over time, over millions of years, tens of millions of years, hundreds of millions of years. We're pulling tons and tons of gas away from the very center of the galaxy, away from this massive black hole that's trying to grow. So right now we have this as one data point, this one surprising, really interesting galaxy. And the question is, will this hold in the future? Will we see more of this? And so ultimately, using all the techniques that I've described to you tonight, I'm going to go ahead and do this for 10 more galaxies, and that will compose basically my entire graduate thesis. Everything going well. So when I go ahead and do that, hopefully we will basically determine whether or not these outflows are significant, if it's actually affecting the way the galaxy is evolving over time, or if it turns out that they're not so important. Then we're going to see if overall these properties are connected to the galaxy. Is there something intrinsic about this? Meaning, do we have if we have a bigger black hole, do we get more mass being pushed out? If we have a brighter galaxy, do we have more mass being driven away? That might be what we expect. That might be what makes sense, but we don't know yet. We have to find it. We have to prove it before we can go ahead and say that. And maybe we'll go ahead and find some other connection that's even completely unknown right now. That's very surprising to us. So, of course, there's always the what else might we find. There's always things that we may not know are out there. So everyone will have to stay tuned for the riveting conclusion in approximately 3 to 4 years. So I expect everybody in this room to be back here. I'll send you out an RSVP. We'll get the calendar date together and get the riveting conclusion to mass outflows in active galaxies. So with that, I would be happy to go ahead and take a couple of questions.
So you talk about the mass outflow. Does it go somewhere? Like, where does it go? And does it go to a point to create another galaxy? Like, is there an exchange of material? Or?
That's an excellent question. So forgive me, I'll repeat all the questions so those on YouTube know exactly what's going on. So the question is, does this material go out of the galaxy? Does it form a new galaxy? Does it just stay there? As far as we know, it's basically staying within the galaxy. It's just being pushed further out away from the center. Those relativistic jets of material actually can extend multiple times the size of the galaxy, and they can eventually, some of that material may find its way elsewhere. As far as we know, all this material is staying basically within the galaxy. It's just being pushed out into the far reaches. And then the next question is, all that energy has to go somewhere. We have all this gas that's just flying everywhere, and that energy has to go somewhere. And so for a long time, it's been thought, well, eventually that gas is going to collide with stuff and slow down. But we should see that. That should come out. Those collisions as gas shocks together should release energy, and we should be able to see that. And we don't see it in the amount that we need to in order to account for everything that's going on. So that's an interesting part as well, is that that's still ongoing. We're not sure where all of that energy is going just yet. There was a question up front here.
Yeah. You said when you talk about how those black lines of the spectrum are caused because of the electron gaining energy from the photon, that causes the upward leap, but what causes the downward leap?
Good question. So we have these absorption line spectrums where electrons jump up because they've absorbed a photon, and what causes them to go the other way. Basically, at the end of the day, we see that electrons like to be at low energy states. So do they have a brain, and do they say, I'm just going to jump down? Who knows? But at the end of the day, what we observe is that they like to be at the lowest energy state. So if they're up there hanging out at the top of the stairs, they're like a little kid, they want to jump down the stairs, right? You tell them not to, but they want to jump down the stairs. And so basically, there's some amount of time that they will hang out up there, and then they will jump down. And for different elements, that will tell you how long they're going to hang out up there. But basically, what we observe is that they want to jump down and get rid of that energy and just send it out again. Question in the back?
Yeah, with respect to your description of this material being consumed by the black hole, causing this release of energy, causing the material around the black hole to be pushed away from it. So that's the self-regulating mechanism. Is that correct?
Yes, correct. So this black hole trying to consume mass, and as it's compressing it and heating it and releasing all this energy, and that energy is driving the material around it away, and that's what's the regulating mechanism. Is the black hole is trying to feed and trying to swallow material, but as it's doing that, it's also creating the energy that's pushing material away, which it's trying to draw in.
Taking it another step, would you call that radiation pressure?
Yes, there's absolutely a component of radiation pressure.
Okay. The next question is, if a black hole is a sphere, is it blowing this mass out in all directions?
That is a great question.
And if you're talking, because earlier you mentioned these beams of energy, so is all of it being tossed out through the beam, or is it being generally blown out in all directions? And if it's being blown out through a beam, if that beam's not pointing out at us, we can still measure it?
Excellent question. So that is a detail that I would have liked to go in, so thank you for asking that question. So we see in some of these galaxies, these very narrow jets that are being shot out, in this case, a good model that fits what's happening is that basically the material is coming out in this slow wide angle cone. So basically you have a cone of material that's being basically blown out. It's not going straight into the galaxy. It's basically coming out in this cone shape. And kind of the reason that we think that might be happening is it fits the observations, and it's kind of a natural consequence of if you have a disk of material around the black hole, as that material is being blown out, it will tend to come out in this more conical shape in what we call bicones. You have a cone in one direction and a cone in another direction. So for some galaxies, that's a very nice fit that matches the data matches the models very, very well. And others, it's much more disorganized. Materials just kind of going where it pleases. Was that everything in your question? Good.
Yeah, that pretty much answered it. Thank you.
Okay, so we'll take a few more, and then we'll go ahead and end the YouTube session. If anyone wants to come up, I'd be happy to discuss more. So let's go ahead and take a few more. Yes.
Yeah, just, you're talking about hot gas. I'm just wondering about, is there also a possibility that some of this mass flow is cold dust that may be charged electrostatically that's grabbing material with it as it goes out?
That is interesting. So the question was, could some of this material also be cold dust that's basically charged and pulling material with it? So in the inner regions of these galaxies, you have so much radiation coming out that we would expect most of the material to be heated. You could have a very dense pocket where the center regions are not heated up, are not ionized. In that case, you would have much colder material that's being dragged out. In terms of just pure dust, dust tends to get destroyed very easily. So depending on the material, dust will basically break apart and just vaporize at 1500, 2000, 3000 Kelvin, depending on its composition. So in the very inner regions, the dust is basically destroyed, but as you go out, that material will cool and dust can form. So that's a good question. So in terms of could a lot of this material be dust? I don't think so, but I don't know. So that's a good thing to check into. All right, why don't we take one more?
Do you ever see elements higher than iron?
Do you see elements that are higher than iron, meaning
You didn't
things...
have anything higher than iron that I saw there.
Right. So as we look at heavier and heavier elements, it is harder and harder to remove electrons. They want to keep their electrons, but as they get very hot, you can rip those electrons away. And so we can see how many electrons have been peeled off, and that tells us about the energies involved. And sometimes we see really, really energized iron that's had dozens of electrons ripped off, which is really tough to explain because it has to be very, very hot. To my knowledge, YouTube viewers, we have not seen anything higher than iron, but I can check with a reliable source and get back to you on that. As far as I know, the highest thing we see is iron. That's a good question.
Would have to be a supernova.
Perhaps, yeah, to produce that. All right, so why don't we go ahead and end the formal questions there, and if anyone wants to come up and chat further, I would love to talk to you. Someone emailed me earlier this evening that one of their children had a question that they were dying to ask me, so please make sure you come up and ask me that. So thank you very much. I really appreciate everyone having me. Thank you so much.